All right, hey y'all, we're making a video. We're learning about electricity today and how to do the calculations that give you information about electrical circuits. So let's go ahead and take a look at the PowerPoint. Now you are going to have access to this PowerPoint on the Google Classroom. So all of this will be covered. We're going to skip through some of it for now. We'll probably come back and revisit it later. For now, we're just going to get into the calculations themselves. So here we go. Electricity, what is it? It's the movement of electrons. It's an invisible force, but one that you can certainly feel. If you've ever felt an electrical shock, you know that it is very tangible. You can't see it though, but by using resistors, we can turn this electricity into light, heat, sound, motion. You're all familiar with putting batteries or plugging something in and turning that electrical force into something else. So here we go. So we're going to skip through some of this atomic stuff right now, some of the theoretical things about how electricity actually works and the chemistry that makes it possible. We'll get into that later. Right now, let's take a look at this one. This is conductors. You know that conductors are something, usually metals, that allow electricity to pass through them easily. Insulators are something like rubber or glass that do not allow electricity through. Those things, let's see, what do I want to say about that? Also, there's semiconductors. Those are things that are used in computer circuits that allow some electricity through. Okay, anyways, here we go. So electrical circuit, that is the basic mechanism of how electricity is transferred and used is through the circuit. And there's three things that are important to know right here. The voltage, which we use with a V, current, which we measure in amps, and we abbreviate with an A or sometimes an I, and resistance, which we measure in ohms, and there's that omega symbol. That's a Greek letter that we use right there. Okay, so here we go. So here's a very basic circuit. You could see the battery right here providing us power. There's an on-off switch, which basically engages the circuit or disengages the circuit. And there's the resistor or the light bulb that's changing the electricity into something that we want, like light. All right, so current flow. So you can read this on conventional current flow, which assumes that current flows out of the positive side of the battery through the circuit and back into the negative side of the battery. This was kind of, this was the conventional way of doing this. This is what people thought. But eventually we discovered that actually what happens is that electrons flow out of the negative side of the battery through the circuit and back to the positive side of the battery. Does it really matter? Not really, but it's kind of funny to look at engineering versus science. In engineering, we actually use the conventional current, which is the wrong one, but we've just been doing it that way for so long that, you know, we just kind of keep going with it since it doesn't really change much about how you design or test things. So anyways, moving on. So there's three things right here. There's the volts, the amps, and the ohms, the voltage, the current, the resistance. If you need to, go ahead and pause the video and write those things down. Probably a great time to do that. And the system that we're going to use as sort of a model for what an electrical circuit is a water and a plumbing system. So right here, the voltage is basically pressure that causes current to flow. So you could see here, if this were water, the gravity, the tank would be pushing water out through the pipe and through the faucet, right? So this is going into our circuit right here. This is the battery where all the electrical current or water is held, and it just keeps on going and going and going until either the tank is empty or the battery is dead, right? So question is, when the faucet switch is off, is there any pressure, voltage? Yes, the pressure voltage is pushing against the pipe, tank, and faucet. So even when you don't have your battery hooked up, that voltage still kind of exists, right? It's like that pressure is always kind of there stored in the battery. When the faucet switch is on, is there any pressure or voltage? Yes, then there's still pressure and voltage, which pushes current through the circuit, right? So when we open that switch, water could start coming out. When you hook up your battery to your Beats headphones, then the current can start coming out of the battery and the headphones can start working. So here you go. So it's that pressure that's caused by the battery or the electrical generator or whatever you have right there that's pushing those electrons through the circuit. So the higher the voltage, the more not force, but the more pressure, the more push behind the electrons there is. So voltage in a circuit right here, the battery provides voltage that will push current through the bulb when the switch is on. Okay, good. That one makes sense. All right, so then resistance is right here, and that's sort of something that pushes back against our flow of electricity. It kind of resists the voltage, right? And you measure it in ohms, right? So you could think of it as what happens to the flow of the current if a rock gets lodged into the pipe. The current decreases. Now, do we have current on it? Did we skip current? Current, oh, here it is. Okay, this makes more sense now. The flow of the electrical charge is measured in amperes, and it's basically how much electricity is flowing. So the quantity of electricity that's flowing. So when the faucet switches off, is there any flow? Is there any current? No. When the faucet switch is on, is there any flow? Is there any current? Yes, right? So you have to engage the circuit in order for that electricity to move. So current is basically it's a quantity, right? It's the amount of electrons that are moving. It's the amount of current that's moving, or if we want to use our water analogy, it's the amount of water that's moving. So note that you could have a very low amount of current and yet still a very high amount of voltage, right? You could have a very high pressure pushing just a small amount of current. So in order to provide the proper amount of power to something, both the current and the voltage is important. So everyone thinks like, oh, voltage, that's what's like deadly, or that's kind of the exciting stuff. And you're right about that. But also the amount of electricity, just the sheer amount of electricity has the potential to be, have a big influence in how a circuit performs or how potentially exciting or deadly it could be. So there you go. So those are kind of the metaphors for the three key parts of a circuit. The current right here is, the voltage is how much pressure there is, how hard the electricity pushes again through the circuit. Resistance is what resists the flow of the electricity, and the current is how much electricity is flowing. Okay, so there we go. Go ahead, make sure to go back, rewatch that, pause that, take notes as needed, and we will move on right here. Okay, resistance, yep. So, okay, resistors are things that create resistance, obviously. Reducing current causes the bulb to become more dim, right? So, okay. So there you go. So a resistor is generally something that creates heat, or it creates light, or it creates sound. It does something that we want, and it takes away electricity. It uses up electricity to become some other type of energy. So here you go. So you can measure the voltage right here, and you measure voltage across a component. So you could see, like, you could measure the voltage across the switch from there to there. So here you go. Out goes your current. You could see what it is across the switch, and then you could see what it is across the resistor and across the light, and then not going back to the battery. And let's see, you would expect to see some difference in voltage across the resistor, right? So you would be able to tell what the voltage drop is across that resistor. Multimeter, yes, we're going to use these. I won't cover that. We'll probably cover that in another video. Let's get into the main thing that we actually need to know to calculate stuff, which is Ohm's Law. And this is the basic one right here, V equals IR. I'm always going to use this one. These are just solving for different things. Like, for example, if you divide both sides by the R right here, then you're just left with I by itself, and you get V over R. V divided by R equals I. Those things. So anyways, it's basically voltage equals current divided by resistance, right? So now, why do we use I for current instead of A? That's a mystery to me. I don't know. And if I were developing the system to make it easy for people to use, I'd probably use A. But we use I. So that's the way it's got to be. So we're going to do a practice problem to solve for that in just a second. So here you go. So you basically cover the quantity that's unknown. I don't know if I'm a huge fan of this chart right here, so I think I'm going to skip through it. Here's a practice problem. We'll do a practice problem in just a second. I'm going to keep talking here. Bear with me, and then we'll solve a couple practice problems. All right, so we know what a circuit is. It's basically linked up batteries and or power sources or electrical sources along with resistors, and it's connected by wiring by things that have very little resistance. All right, so there's two ways to really wire something up. One is in series, where this is a perfect example of a series circuit. Everything's just connected in this sort of circular pattern, right? If electricity flows into one, then it flows into another one, then it flows into another one. So if you think about it, all of the current is going to be right in here, right? Here's a parallel circuit right here. And if you think about it, okay, here is your series and parallel. So let's say that this one is the battery. So then if things come out of the battery right here, your current comes out the battery, then it has three pathways it could go. It could go there, it could go there, and it could go out to there, right? So there's different pathways for the electricity to flow in a parallel circuit. So this has a lot of advantages. This is like, if you think of a string of Christmas lights, maybe you've never, I don't know if you've ever put up Christmas lights or not, but sometimes it's frustrating because if one bulb goes out, the whole strand goes out. I actually just replaced my grandparents' Christmas lights this week after Thanksgiving, and we were missing one bulb. And rather than like try to find a replacement bulb, what I did was I just stuck the two wires that were still there. I just stuck them together, and it made it work again, right? Because one little missing gap right here creates a whole gap in the circuit that keeps things from flowing right there. So if these were really expensive Christmas lights, maybe they would have wired them up in parallel so that, you know, one bulb would have no effect on the rest of the system, or would have, you know, wouldn't have a detrimental effect on the rest of the system. Anyways, okay, so those are the two ways, either one single path or multiple paths. So there you go. Kirchhoff's law right here. So now this is important right here. The sum of all voltage drops in a series circuit equals the total applied voltage. So basically right here, okay, so if you look at this, if this is our battery right here and this is pushing current around, then current has three pathways it can go through, right? So if you were pushing 1 gallon of water per minute, you might expect like a third of the water to go in there, a third of the water to go in there, and a third of the water to go in there. So you're going to basically have 1/3 of a gallon of water per minute, right? It kind of works the same way with the current, where now it might not get exactly a third depending on how much resistance is in there, but you're going to get a separation of the current right there. So if you add up all the branches, you're going to get the total current right here. Whereas the voltage, that pressure that's pushing it, is going to stay consistent. Okay, so the voltage right here, voltage law is saying that in a parallel circuit, you add up the currents, but the voltage stays the same. And right here in a series circuit, you have to, let's say this one's the battery, right? And it's pushing around. So all that water, 1 gallon of water is flowing around that circuit, right? 1 gallon of, or whatever, 1 ohm of electricity, or not 1 ohm, whatever, 1 amp of electricity is flowing around that circuit, right? And it's not going to get split up into the thirds, but our voltage is going to get split up, right? So the voltage right here, maybe 1/3 of the voltage consumption happens here, 1/3 of the voltage consumption happens here, and 1/3 of the voltage consumption happens there. So that's what that's saying. Okay. Yes, so here's an example of a series circuit. Here's the Christmas tree light example. If this bulb burns out, this one's going off too. All right. So yes, okay. Now the final example is resistance. Where are we? Series circuit, yes. I'm sorry, guys. Let's see. Where am I trying to be right now? Okay. So characteristics of a series circuit is right here. The total resistance total is equal to the sum of all the resistances, right? So right here I have 220 ohms plus 470 ohms plus 1,200 ohms or 1.2 kilo ohms right there. The total amount is going to be 220 plus 470 plus 1,200 ohms right there. You just add them up like that. Now, if I go, okay, so series circuits, yes, we're going to skip this for now. Series circuit, parallel circuits. Okay, now parallel circuits are much more complicated. The resistances are rather different. Here is the total resistance so we have our same thing right here, 1 over 470, 1 over 220 or 2,200 ohms and 3,300 ohms, and you actually add them up right here, and that you divide them all by you take the inverse of each of the resistances, then you add them all up, then you take that and you take the inverse of the whole number. So fear not, we're going to do an example right here, and I think I'm going to go ahead and shut off the PowerPoint right now. I know we skipped through a lot of the math, but I think most of it's pretty understandable. This right here, we're going to do a couple examples, and then we're going to move on. Hopefully this will be enough to get us started at least in computing some of the things that we need. So I'm going to go ahead and switch over to the tablet right now. Give me just 1 second here. Let's see. Let's go ahead and kill this recording. Okay, so now let's say we want to solve for something in a circuit. So we'll just do one easy example right here. We know that V equals I R. Sorry for the messed up R. Let's say that voltage equals 6, I equals 3, and we want to know R equals what? Okay, so we're just going to simply substitute it in and solve. We're going to say 6 volts equals 3 amps of current, and we don't know R, but it's easy to find R just by dividing by 3. There we go. That cancels out. We're left with R equals 6 divided by 3 is 2. Okay. Very, very good. Okay, so that was easy. Now the more complicated thing is solving for resistance. So right here we have resistance total. So we're going to draw us 2 circuits right here. Here's one circuit right here. And this is the symbol for resistor. It's like a squiggly line like that. So here is resistance 1. Notice that it's in series. And to keep things easy, let's just do like 10 ohm resistor and a 20 ohm resistor right like that. Okay. So then we say RT equals 10 plus 20 equals 30 ohms. Very, very easy when they're in series. Not so easy when they're in parallel. So let's go back, get rid of some of this stuff. Yep. Just go ahead and erase all this. Yeah. Give us a nice blank screen. Oh, yeah. Go back, because we're going to need a little bit of room here to compute our parallel circuit. So here we go. So let's see. We got our battery right here. Oh, this is our symbol for a battery, right, like that. And then we have our 2 channels of our parallel circuit. There's our resistor, goes back, and then we go down here. Here's another resistor, goes back to there. Let's say that this one is our 10 ohm resistor, and this one is our 20 ohm resistor, like that. Okay, so now we know that 1 over total resistance equals 1 over R1 plus 1 over R2. All right. So where am I? Okay. Yes. 1 over RD. Okay. So we're going to do this. We're going to solve for these like this. 1 over RT equals basically 1 over 10 plus 1 over 20, like that, right? So that's going to equal, and I could use decimals, but I think probably better to use fractions. So I'm going to find a common denominator. I'm going to say that that is 2 over 20 plus 1 over 20 equals 1 over RT. Okay, so that equals 1 over RT equals 3 over 20. Okay, so now at this point you're almost done, but now basically what we need to do is we need to take the inverse of both of them, or what else we could do is we could solve by cross multiplication. Since everyone's told me they love cross multiplying so much, let's just go ahead and do that. We'll take our cross multiplication right here, and we'll say that 20 equals 3 times our total, resistance total, and then we'll divide by 3, divide by 3. So resistance total equals 20 over 3. Or what is 20 divided by 3? I don't know. I can't even do that right now. I think it's 6.6 repeating, right? So 6 points. So it's kind of strange that your total resistance is actually less than either of the individual resistances, but that's the way it works. All right, so I'm gonna leave you there. Hopefully that's enough to at least get some of the practice problems done, and we can work on these a bit more. Anyways, thanks for watching the video, and we'll see you soon.